Right, AVR serial programming. Now, in the previous chapters where we start to talk about the AVR resources and how are we going to use these resources like timers and the interrupts were two of the hardware resources in there. Now, another important one is serial port programming, which we need to communicate with the outside world, like with the PC or some other peripherals. So here is the outline of the lecture. We'll talk about the difference between serial and parallel data transfer, the different terminologies like simplex, duplex, full duplex, advantages of serial communication or parallel, asynchronous communications, how data is framed and sent it to from one side to the other, data transfer rates, how do we do the calculations, and some standards that that we are using and that they're still on the literature. And then we'll start to talk about AVR specific features like UBRRs, the baud rates, and the data registers and the control registers in AVR that can be used in order to do some serial communication. Okay, so microprocessors, microcontrollers, they have to communicate with the outside world, and they are doing this with one or many bite-sized data chunks. And for some devices like printers, they are using 8-bit data transfer in parallel route. So if probably you don't remember these printers that we were using parallel ports, they work if the cable is not too long. That's one thing. And 8-bit data path, the ports or the cables that we are using, they are quite expensive. We were using, actually, we are not using them anymore. And because of these parallel wires, they have got a distortion, coupling, or noise problems. Now, when we think about serial data, it's just 1-bit data path, so it's just one wire. It's cheaper, and in serial communication, we are using parallel load, serial out shift registers so that we can convert the parallel data into serial, or the serial in parallel out shift registers where we can convert serial data into the parallel. So as I start to mention that serial and parallel terminologies, computer transfer data in two ways, which is parallel and serial. Now, as I already mentioned with the printers, in parallel, data transfers often 8 or more lines, so more wires over there. And they used to transfer data only few feet away. They are fast, but if you have a longer cables, because there are 8 wires in there, you might get a distortion or coupling or noise problems. Now, although a lot of data can be transferred in a short amount of time by using many wires, the distance cannot be great. So in order to transfer to a device located many meters away, the serial method is used, and in embedded systems applications, we generally focus on the serial communication. Now, in serial communication, the data is sent 1 bit at a time, in contrast to the parallel communication, and the data is sent a byte or more at a time. So we are just shifting data serially. So parallel devices, as I already mentioned, printers, the information is simply grabbed from the 8-bit data bus and presented on the 8-bit data bus of the device. So as I already mentioned, the cable shouldn't be too long, and long cables can diminish and even distort the signals, and 8-bit data paths, they are expensive. So they are not used in there and you cannot find them on the market anymore. All right, so let's see how we can compare serial and parallel operations or the communication. So these are all the things that I have already mentioned. Now you can see the serial transfer and parallel transfer. So parallel, as you can see, many wires from the sender to the receiver side, but the serial is just one bit wire. And you can have a longer wires. It's cheaper. Some of the protocols that we have got, UART, I2C, SPI buses, these are all supporting the serial communication. And another example that we are sending with asynchronous serial bits. So from the sender to the receiver, as you can see, whenever the clock is changing, starting from the most significant bit, going to the least significant, we are sending one bit at a time. But in parallel, on the one clock cycle, all the data is sent parallelly. And you can see this on the other side where we have got the computer, we have got a parallel data bus. So what we do is we use like a UART, is a protocol, one of the protocols, which will convert the parallel into serial and it will shift out one bit at a time. And once again, the parallel data, it's sent parallelly. You can send 8-bit data or 16-bit data at a one clock pulse. Now, for serial data communication to work, the byte of data must be converted to a serial bits, as I already shown over here, using a parallel in serial out shift registers. This is one of those. And then it can be transmitted on a single data line. And at the receiving end, there must be a serial in parallel out so that the parallel data can be placed on a data bus. Now, data transfers or the examples of the serial buses, let's say, there are many of them on the market at the moment, or the protocols that we are using, RS-232, 422, 485, I2C, SPI, microwire. So these are different communication types, and they have got different features like the number of wires used, the communication type, the speeds, which are quite important, and the distance that they can be, and so on. So you can find them in the data sheets depending on the microcontroller that you are using. They might have a different protocols that you can use over there. Okay, so we have got different types of transfers. Simplex data can move only in one direction. So only from transmitter to receiver. That's the simplex transfer. Half duplex, you can move data in both directions, but not at the same time. So you have to wait one of them to finish the transmit, and then the other side can transmit the data. And the full duplex, you have two-way communication. Either you send or receive, you can do that at the same time. So full duplex is easy to use. Now, once again, three ways to transfer from computer to peripheral. We can demonstrate unidirectional, simplex, half duplex. You can see bidirectional, and the computer is sending the data. Peripheral needs to send an acknowledgement back. Okay, I have received the data required, but whenever this one transmitted, finished, and then this can send the acknowledgement. And in the full duplex from computer to peripheral, you can send all the data from one side to the other. That's the difference between them. Now, when we talk about serial communication, we actually have two alternatives. Either it can be an synchronous or asynchronous serial communication. So if you do remember from logic design, synchronous works with the clock, asynchronous works without the clock. So clock pulse is not transmitted, and two sides should generate clock pulses independently, but they have to be synchronized somehow, or there will be a protocol. Otherwise, it might be a clash and there will be some problems over there. And we are sending single byte at a time. And that general, this is called universal asynchronous receiver transmitter, UART. And the synchronous mode, we have got the clock pulse should be transmitted with the data, and the master side generates the clock, and block of data at a time can be transmitted. And Atmega 128 has got both universal synchronous and asynchronous receiver transmitter sub protocol and the feature which is called USART. So if you want to do a communication across an asynchronous device, now the data coming in at the receiving end of the data line in a serial data transfer is all zeros or ones. So, we're just sending a data, let's say 1011011001, for example. We are sending this out. So it is difficult to make sense of the data unless the sender and the receiver agree on a set of rules, which we call them protocol, and on how the data is packed. So if there's a start bit, stop bit, parity bits, and so on, and how many bits you are feeding into one pack. And we have to specify all of these in the asynchronous serial communication. So it's hard to synchronize between the transmitter and receiver. But if we had the good protocols, like how the data is packed, how many bits, start bits, end bits, the center bit frame, so this could be easier. And you all need to know is where the start bit is. Generally, it's in the falling edge, and how fast the bits are coming, which we can calculate the baud rate. Now, asynchronous serial data communication is widely used for character-oriented transmissions, while block-oriented data transfer uses synchronous method. And in the asynchronous one, each character is placed between the start and the stop bits. So we have got start bit, stop bit, and we have got the data in between them. Okay. And this is actually called framing. So in data framing for asynchronous communication, data like an ASCII characters are packed between these start and stop bits. And start bit is always 1 bit, but the stop bit can be 1 or 2 bits in AVRs. And the start bit is always 0, and the stop bit is always 1. So these are some of the things that we need to know. You can see the start bits when in the polling edge, there's a low. So we have got the sample data bits, and then we'll have the stop bit. Now, when we consider the asynchronous USART, there are 16 internal clock to sample the start bit. This is something important, and it's related with the USART. Now, what we need to take care over here, the incoming data is continuously sampled. So it's sampled, and we just need to look at if the falling edge is detected. So whenever it detects the falling edge over there, what it does is the receiver waits for 6 clock cycles. So 1, 2, 3, 4, 5, 6 up until here to begin the sampling. So 1 clock before the expected center of the start bit. So here, because that's the center, 1 clock before is the 8th in this case. So 3 samples are taken. So 8, 9, and 10 are taken as the 3 samples. And what they are looking over there is, because after the falling edge, because this is the start bit, which has to be 0, it has to make sure that those 3 samples are low. Okay, so if 2 or 3 are detected to be high, the search for another falling edge is started. So if you are detecting high over there somewhere, then it has to look for another falling edge. That means it's not the start bit. Now, if the result is low, that means the sampling over there is done and the result is low, then what it does is the start bit is validated, and data sampling begins 16 clocks from the center of the start. Okay, so starting from here, it will count 16 clocks and it will start sampling the data. So what it does is it has to revalidate again with each data byte, and synchronization happens on each byte. Now, as I already mentioned, the framing is we have got the start bit, which is bit 0, and then we have got the bytes of data starting from D0 to D7, least significant to most significant bit. Then stop bit, it can be 1 or 2 bits, which is going to be high. And the characters can be between 7 to 9 bits, or parity bit can also be added. It's optional. It can be configured. And for example, in this one, ASCII A, which is for 1, is send. So 0100 is 4, and 0001 is 1, and this is what we are sending from one side to the other. Now, one thing that we need to be careful, or let's say we have to consider taking into account, is the data transfer rates. Now, the data transfer in serial communication is bits per second. Now, or bits per second is known as the baud rate. So the baud, or the BPS, bits per seconds, they are not actually necessarily equal. Okay, this is because the baud rate is modem terminology. It's coming from the modem terminology, and it is defined as the number of signal changes per second. And in modem, sometimes a single change of a signal transfers several bits of data. So what will happen is the single change of a signal transfers several bits of data. And as far as the conductor wire is concerned, the baud rate and the BPS are the same. And for this reason, we can use BPS and baud rate interchangeably. So how do we do the calculation? Now, actual transfer rates, which is bit per seconds, we have to know the number of data bits, and we have to know the number of frame bits, and we have to multiply that with the baud rates. So the baud rates are generally given because each microcontroller or the communication line or a medium has got the baud rates. So we can use that byte rate given and we can do the calculations. So let's see an example. Consider an asynchronous serial I/O system with no parity, one start bit. So one start, 8 data bits per frame, 8 data bits, and one stop bit with 9600 baud. So we have to find out actual data transfer speed, data rate, and the character rate. Now data rate, so let's change the color. Data rate is what? As the equation is telling, the number of data bits, we have got 8. So the number of frame bits, 8 plus 1 plus 1, we have got 10 bits in total, times 9600. So this is giving us 7680 bits per second. So that's our data rate. Now, in order to calculate the character rate, this was part A. So the character rate is, we know the baud rate is 9600, okay? And we know that there are 10 bits in the frame. 10 bits per character. Now this is going to give us 960 char per second. So we can send 960 characters in 1 second. So these are the simple calculations that we can make by hand, and we can calculate them. Now, RS-232 standard. Now, in the early days of these communication lines and the invention of these protocols, in order to allow compatibility among the data communication equipment made by various manufacturers, they have interfacing standard called RS-232, one of the oldest ones, which was set in 1960. And this is then modified to 232A, 223B, 232C, and 1960 bar 69, and respectively, it goes like that. So 232 is one of the most widely used serial I/O interfacing standard, and this standard is actually used by the PCs and the numerous types of the equipments as well. And but as this was sent long time ago, when there was a TTL logic family at that time, the input and output voltage levels are not TTL compatible. So in RS-232, 1 is actually represented by -3 to -25, while bit 0 is +3 to +25 volts. So making -3 to +3 undefined. So in order to connect any RS-232 to a microcontroller system, we must use a voltage converters like MAX232, which I'm going to show you in a minute, to convert the TTL logic levels to the RS-232 voltage levels and vice versa. So we need some kind of a bridge or a converter in between the device and the microcontroller, or we generally call them line drivers. That's the technical definition of it. So RS-232 define signal levels, connectors, pin assignments, some other things in the protocol, and it's a serial interface connector plus electronics. Original version was 25 pins, which is known as DB25 connector, but then it's converted to 9 pins, and I will show you in a minute how it looks like. So this DB25, which is a 25 pin, but nowadays the DB9 is used, and you just need to use only 3 pins over there, which are receive, transmit, and ground. Okay, and USB-C has mostly replaced the serial communication ports on PCs, but RS-232 is still alive and active in embedded activities because it's cheap. So in the RS-232 standards, we also have data communication equipments in 2 types. Data terminal equipment, DTE, which is the initial source and the final recipient, and also data communication equipment, which is DCE, which are the functions to establish or maintain and terminate a connection. So coding and decoding and drivers and so on. Now, one important thing, we have to know that we can use only 3 pins, and you have to know the pin numbers when you are connecting it to the AVR. And the important connection is the null modem connection. So you can say that the device or the peripheral or the PC is DTE, data terminal equipment, and on the other side you have got an AVR as a data terminal equipment. So the TX, the transmitter pin on one side has to be connected to the receiver pin on the other side, and the transmitter pin on the AVR, let's say, has to be connected to the receiver on the PC side. So this is called null modem connection, and this is how we generally connect AVR with the PC. Now, when we are having these serial communication, we have to be careful how the protocols are working and what will be the flow control. Now, protocol is just a set of rules making the connections and the messaging. And the flow controls, they are just the methods of stopping and starting the data transfers. So we have to control how the data is going to be transferred. And there's a acknowledgement, not acknowledgement, flow control. At this point, transmitter waits for the acknowledgement signal from the receiver before sending the next data, because receiver needs to say, okay, I have received the data, I'm ready for the next one. This is one of those. Cyclic redundancy check, longer check field than the one parity bit, so you can have a CRC checks at the end of each package. It's more sophisticated error checking. It tracks message history and so on. X on, X off flow control. So receiver initiates or stops transmitter by sending on and off message signals. And the break signal, as the name suggests, it breaks or it aborts the transfer in the midstream or wake up sleeping receiver. So these are some of the protocols or the flow control that we use in serial communication. So how is that going to be connected to AVR, and how are we going to use AVR resources? That's what we are going to see next.